Hey everyone, Dave here again. We're now going to move on from our electron configuration stuff and see how it actually fits into why particular elements react. And we're going to start with the simplest example, which is ionic bonding. So I'll just fire this up here. We're not going to worry about the lecture objectives. You can read those for yourselves later. Now we're going to start just by reminding ourselves of the electron structure of a particular group of elements. So we'll start with the alkali metals. You can see here we've got them listed, and of course you know they have these particular electron configurations, and most importantly their chemistry is going to be dominated by them losing an electron to look like their nearest neighbor noble gas. I think what I'll do is I'll just put on the pointer options, go to felt tip pen, and ink color black, which I prefer. Okay, if you look at the halogens, we already know this, we've been through this kind of stuff. We've got fluorine here, there's its electron configuration, chlorine, etc. You can see here that they're one electron short of their nearest neighbor noble gas, so all of these elements have chemistry that's dominated by trying to pick up an electron. So what I'm trying to do in this lecture is try and fit it all together so you can see how you end up with particular things reacting and compounds forming. Just point out to you that the reason why things again are doing this is because they want to get to a stable situation. In other words, they want to get to a lower energy value. It's a bit like me asking you if you were holding a stone or a rock or something and you wish to drop it, and I said to you, well, if you drop it, it's going to land on your toe. Of course you know it's going to do that. It's going to go downhill because that's at a lower energy level. And when chemicals react, they do exactly the same thing. They're trying to get to the lowest and most stable, lowest energy level and most stable position possible. And of course I've already pointed out to you that that electron configuration is actually what determines their stability, and everything's trying to aspire to look like a noble gas. Now I need to point out to you some terminology, and the terminology revolves around these three terms basically. There's valence, valency, well, four terms really, oxidation number, and valence electrons. Now there's another way of doing this other than just memorizing them. Once it's in your head, you'll know what they mean. Okay, so the first one is valence electrons, and that's the definition there. It's the electrons in the outermost shell, or the number of them. So, and they're referred to as the valence electrons. So, for example, there's one electron in the outermost shell. That's the highest principal quantum number for lithium. So its number of valence of electrons is 1. Whereas for fluorine, it's actually got 7 valence electrons. In fact, I can just zip back here. You can see here there's fluorine, 2 and 5. It's got 7 valence electrons. And if I showed you lithium, it would be obviously 1 valence electron. Now, the number of, when things react chemically, what they're doing is they're essentially swapping electrons. So the number of electrons that are involved in the swap is referred to as that particular element's valence. The other word that's used is valency, which is the same thing. So I'm just going to always use the word valence. And you'll see that these terms are slightly different. None of this is going to make perfect sense to you until I illustrate it by example, I wouldn't imagine. The oxidation number, it actually refers to the valence of the thing. So it's asking the question how many electrons are being swapped, but it's also asking the question whether they're being gained or lost. So let me give you an example here. We look at lithium and chlorine. The valence of those two elements is 1. Reason being is lithium will tend to lose 1 electron to look like helium, and chlorine will tend to gain 1 electron. So the valence is 1, there it is there, right? But the oxidation number for lithium is +1. It actually means the plus here means that it's going to get rid of an electron, and for chlorine it's -1. Now we'll get that terminology out of the way. Let's start looking at examples. Here's an example of what we mean by valence electrons. So these are the ones that are going to be in the outermost shell. For magnesium here you can see it is 2. There it is there. And for silicon you can see it's 4. There it is there. Alright, now if something gains or loses electrons so that it can look like a nearest neighbour noble gas, it's then no longer a neutral atom, and we refer to it as an ion. That is, it's being charged. And the bottom line here is if something picks up an electron, it's got an extra negative charge associated with it, so it's a negative ion. If it loses an electron, it's then going to have a positive charge. It would be a positive ion. There's just a little summary for you. Although this last point's an important one to remember. When things gain or lose electrons, the electrons have to go somewhere. And when they're reacting in such a way that if something loses an electron, something else is gaining one. And that's an important point. Alright, let's have a look at ion formation, just to illustrate again what's going on here. If we've got sodium, you know it's got 11 electrons, it's got atomic number 11, therefore it starts off the sodium atom with 11 electrons. It's got 1 valence electron, there it is there, and it's going to try and lose that thing to look like neon. So when it does that, there we go, it's now got 10 electrons. It's still got the same number of protons in the nucleus, 11. So you've got 11 positive charges in there. You've got 10 on the outside that are negative. So you've got 1 positive charge in excess. So the charge of sodium is 1+. Okay, let's illustrate how things actually react then in terms of electrons. Here's an example where again we've got sodium. There's its electron configuration. It's going to want to lose that one. Chlorine here is going to want to pick one up. So if it picks that up, that then becomes 3p6, and it's got a stable noble gas electron configuration. There it goes. Sodium loses one to look like neon. Chlorine picks one up to look like argon. Okay, so now we've got sodium with a 1+ charge. Remember, it's lost 1 electron. By the way, let's use another bit of terminology here. God, I wish I could write with this thing. Okay, any positively charged ion is called a cation, so that's a sodium cation, or you could just call it a sodium ion. This one over here, the chlorine, is an anion. There we go, and it's 1-. Alright, now somehow you've got to write down the formulae for ionic compounds. To me, the easiest way to do it is just to ask yourself what the valence of the compound is. So, first of all, we better just think about how you work out valencies. Well, let's just look at this example here. We've got sodium. What's its valence? Well, it's got 11 electrons. There they are. It wants to lose 1 so that it ends up with an electron configuration of neon. So therefore, if it wants to lose 1, sodium's valence is 1. Chlorine wants to pick up 1 electron to look like its nearest neighbour noble gas. Therefore, chlorine's valence is 1. Neon is a noble gas, therefore its valence is 0. And if you look at calcium on the periodic table, you'll see that it needs to lose 2 electrons to look like its nearest neighbour noble gas. So the valence of calcium is 2. So once you have a little bit of practice with this, it doesn't become too hard to work out what the valence of particular elements is. The question is, how do you use it? Because you want to use this to work out the formula of ionic compounds that are formed when things react. Oh, by the way, very importantly, I should mention, if it's not already obvious to you, that because you're getting this give and take relationship with these sorts of compounds, metals are always things that give electrons, non-metals are things that take electrons. So these types of compounds only form between metals and non-metals. Alright, let's look at how we'd work out the formula for a compound. Okay, so for example, if we've got calcium and chlorine reacting, what you do first is you write down the symbol for calcium, there it is, the symbol for chlorine, there it is, and then what I do is I write the valence there for calcium and there for chlorine, and then I swap them over like that. And that actually gives you the correct formula. So the formula for calcium chloride is CaCl2. Now you might think, well, why is that? Why isn't it just Ca? Well, the reason, of course, is because each chlorine atom can only pick up 1 electron. But I have calcium which can donate 2. So if you want, you could write it like this. Here's calcium. It's going to give 2 electrons. I'm going to write 1 electron here and 1 electron here. And I'll need 2 chlorines to pick up 1 electron each. So you can see the formula for calcium chloride is CaCl2, because there's 2 of them here.